Hello, my name's Paul Mackin and welcome to this presentation on the 3D Master Experience, based upon the Dassault Systems 3D Experience platform. First we'll look at the existing process, which is typically defined in 2D. We want to reassess that and describe how 3D will become more and more important, not only for geometry, but also for specification. We will dive into the business challenges faced across multiple industries and disciplines, and where they need to make some changes. We'll then review our answer to these challenges, and we will quickly review some customer cases. Finally, we'll recap all of that in the context of the business benefits. So first, let's think about the current process. The process that is really deployed across most organizations. Globally, 2D is still the master, meaning 2D is the reference against which the definition is checked. Why is that? Well, because today 2D is still the language people are using. It's standardized, people are familiar and comfortable with it, and indeed the language has evolved with the disciplines and cultures of the organization. 2D is the reference which is produced during the product development across all phases from conception to production. And from each of these phases, which are quite sequential today, there is a specific and formalized way of identifying and creating specific 2D deliverables, which correspond to the phases of the product development cycle. But nevertheless, at the end, using 2D as a reference has some failings. And there are some new challenges which people are facing where 2D cannot deliver the improvements which people are seeking. Here we use the picture of a guy who's working in 3D on a laptop. But when an urgent engineering change is requested, perhaps just a dimension value or an annotation, sometimes people feel more comfortable just to draw it physically, rather than perform the modification to the original data. So here we're creating a breakage. And what we're seeing globally in companies who have implemented 3D techniques, there are many such breakages across many phases of development because there is no continuity of process. And where such drawings are isolated, it becomes extremely difficult for a company to propagate a change, say from detail design through to production. And this is where people are losing a lot of money and a lot of time. If we look at the processes over the past 40 years, of course, everything started with 2D drawings. And in the last 2 decades we have seen major progress where people have seen the value of 3D to design and to create the digital mock-up, but at the end 2D remains the master document, which people will look to for the product definition. So now let's look at the business challenges which those companies are facing today. One example is quality. Here we see a wire harness which is too short and cannot connect. This is common, and it was a story on a high-profile aerospace project where the poor fit of the wire harness, jointly developed between multinational participants, led to a hugely expensive recovery plan and delays to the program. In architecture, it's not unusual to see absurd results realized in production, based on what is described in the drawings. A door blocked by another structure, for example, or a staircase which leads to a dead end. Have you ever bought a car, for example, and after 6 months discovered that the quality created is not sustainable in the mid-term? In this case, a glove compartment won't close correctly because of incorrect tolerances and adjustment. And worse, of course, is safety. When quality impacts safety, there can be a tremendous danger and negative impact. A few years ago we had a famous automotive example where the car failed an important evasive maneuver test, resulting in major modifications and redesign to the chassis in order to recover, and lost sales in the interim. So what are the business impacts of keeping the 2D master process? First, working in a 2D master process means that there are a lot of documents. A lot of different pieces of information that you need to provide, even if you're working in a database. The challenge for engineers is, how can they find the right information? Many of our customers tell us that today they are spending too much time looking for information, searching for the right information. The impact on programs is huge. The second impact is that when there is lots of iteration and change of specification, detailed design, of manufacturing process or of production, they have to identify and modify the drawings which are provided. The scale and cost of this effort is so huge today that it extends the program itself. And last but not least, the effort involved in continuously trying to keep drawings up to date is so huge that it simply never gets done fully. There are product quality and customer satisfaction issues directly resulting from the ongoing use of unsynchronized and incorrect 2D documents. It's well established that the later in a program a change is discovered or made, the more expensive it is. So the challenge is, how can we anticipate to find the problems earlier and make the changes sooner and at lower cost? So now let's explore in more detail the root causes of the negative business impacts of 2D master. We have summarized this in 4 points. The first is to say that when you start design of any product, it is very, very rare to start from scratch. You almost always start from something existing. With 2D master, of course, the existing is not simply a single piece of data. Existing can come from 2D or 3D or in multiple formats. So one of the challenges for people who are starting a new project is, how can they work on data coming from different sources? The second aspect is that there is no continuity today among the number of phases of product development and the number of stakeholders who need to contribute to the development and the decision making. Today there are many different phases which are completely desynchronized and where at the end there is breakage. The progress today from concept to detail to manufacturing to production is quite manual. It is linked to the expertise of people, it is linked to the knowledge of people, and it's not automated. Drawings are still the reference in ensuring people understand the connections between the phases of product development. And something very simple which is still missing, and customers are spending lots of money on, is the misinterpretation that drawings can deliver. A simple example here. Is it a diameter or is it an offset? In 3D, we still have a cylinder or a rectangular structure, but the drawing is missing the information. How can you make sure your drawing is self-contained with all the information required to fully define the product? Today, there is no answer to that in 2D, because 2D has inherently elements which cannot be shown. 3D brings completeness and precise definition. And the last item is, as you're working with lots of drawings in parallel, depending on the phase of the project, the cost of maintaining the integrity of these drawings during the change process is huge. If you manually change one drawing, it becomes immediately desynchronized from the original data. If someone then makes a change in the 3D, the drawing is no longer aligned. So the cost of resynchronize everything is very large indeed. This list of 4 is not exhaustive, but it gives a good indication of where the challenges are. So how do we answer these challenges? Today, we have moved from 2D design and 2D master, and our solution supports our customers in 3D design and 2D master. But in parallel, we have introduced the concept of 3D design and 3D master. This means no more external drawings. We're able to define directly in 3D the same structure, annotation and definition and functional description to reflect the total definition of the product. So what is the 3D master concept? Well, the key element is that there is one single reference in 3D. Of course, this single reference contains the geometry, but much, much more. It contains 100% of the product information. accurate and annotated geometry, not only geometry but descriptive text. It's compliant with all regulations and standards because we are reapplying the rules that exist in 2D in 3D. And it can be directly reused for manufacturing and work instruction in the downstream applications. 2D is available, but it is only a presentation of this 3D specification. This single definition is integrated through the 3D Experience platform with one single database and available to anyone, anytime, anywhere. And of course, this maximizes our ability to reuse data because we're able to mix the environments of 2D and 3D data in this single instance. And it directly feeds the downstream applications like manufacturing. So if we are looking at the end-to-end process coverage, today we see that it's quite sequential with many breakages between the phases. And what we are introducing with 3D Master is the continuity from conception to production. With one single 3D reference definition, 3D Master is at the heart of this to capture the information which is individually defined. We can show the value across the whole process, unifying the different phases, but we can also show the value to each individual phase. If I refer now to the global product development community, all products are developed in a complex ecosystem of partners, suppliers, regulatory authorities and consumers, then 3D Master helps this too. Exchanges can be based on the single 3D format, but you may not wish to force your suppliers to move to 3D. They may recognize the benefit of doing so. For example, a major aerospace company has been able to work with the regulatory authority, delivering 3D data only for maintenance validation. 3D Master is not simply a Dassault Systems approach. It is a Dassault Systems term, but the concept is valid across the industry. And remember, as a reminder, 3D Master doesn't mean no drawings. It means we have one single 3D model as the single source of product information. Where there is 2D, it's only a representation of this 3D information. So now let's look at the 3D Master value proposal for each phase of the design process. It's important to explain that 3D Master is a global approach, and the more it's used across the end-to-end process, the greater the benefit. But we can also demonstrate that 3D Master delivers benefits locally to each product development phase. So let's start with the conceptual design phase. Let's watch this demonstration, which features a motorcycle design, and as we stated earlier, design never starts from scratch. Here we have a conceptual architect who needs to design a new bracket to support the two-cylinder engine on top of the motorcycle frame. First, we're able very simply to work in 3D in the context of the complete motorcycle, linked to a single database. And here we've made a section view, so you can see we can work just as if we're in 2D, in transparency with the 3D behind us. Here we'll deliver the curves which represent the motorcycle frame edges, which will be the basis of where the bracket is supported. So the architect of the conceptual design of the bracket is just drawing in 2D, as if he were in a drawing, using the projection of the frame. It's important to understand that the frame edge that is part of the bracket is associative to the 3D models of the frame. From that, we're going to define a yellow point here which shows where the bracket is to be connected. The designer knows that in perhaps 1 year from now, he will have to deliver a new engine, which might perhaps have 3 cylinders. But this engine does not exist in 3D, only in 2D. So here we have imported a DXF format. You can see that he can very quickly decide to design a slot in the bracket which can accommodate both the existing 3D two-cylinder engine and the forthcoming three-cylinder engine modelled in 2D. And from that profile, which has been created in 2D and 3D, he's able to create his first 3D rough shape with a pocket for the slot. The architect is not a detail designer, he's just taking care of the functional context of the bracket, being able to support both engines. And what we are showing here is the associativity created even in conceptual design. Here we have changed the position of the hole in the two-cylinder engine support, and by updating the part, the bracket slot follows the shape. So what we've been able to show here is that 3D Master in conceptual design delivers the flexibility to draw in 2D in the context of 3D, delivers simplicity in importing DXF and creating a model with associativity should any engineering change come, and beginning to prepare the single model definition created using multiple sources. Lots of flexibility for people used to working in 2D. Let's look now at the second phase, which is detailed design. In detail design, we have two ways of working, on single parts or on assemblies. So let's start with part design. We're now going to work as a detail designer who from the conceptual design has taken and fully detailed the part. You can see all the filleting, drafts, pockets and chamfers which complete the geometry. Now in 3D with this single model, we're able to define views and create, based on this view definition, for example, datum feature references. Here we can create a radius with a tolerance based on the outer shape of the body. Each time you create a tolerance, the Semantic Tolerance Advisor checks that it's relevant based on the 3D geometry that you're selecting. Let's show an example in the second view, which is a view where I want to make a section, and you can see the hatching in 3D. Here the advisor provides information on what you can do. We will return to the advisor on a specific case, which will demonstrate its efficiency. Here we're creating a roughness symbol on part of the bracket which will be welded to the frame to ensure that the surface is correctly prepared. And here the advisor automatically brings you the slot dimensions and the tolerancing, which have been defined by a formula, for example, between the slot definition and the external radius. We can now create a second section view in a different plane, and from that we just copy the definition of the slot, perpendicular to the first one, to define the width and diameter of the hole, and also the fact that we want to position it in relation to the two references, A and B. And of course we can annotate it, for example, for surface treatment. Here we're defining a capture, which is where I want to filter the annotation structure so it can be viewed as if it were a drawing. So that's the definition of one part. We can now reapply the same functional description or schema to another part, which is of the same family, but has, for example, different dimensions. It's just a copy-paste, so I don't have to waste time repeating the creation of views and annotations. So now let's look at design in the context of assemblies. Here we have removed the visualization of the motorcycle frame in order to focus on what we're doing at an assembly level. Here we're applying a balloon to the bracket at the product structure level, referring to the part itself. And another for the cylinder head support. So in assembly mode, we're able to create annotations, and we can also create views. And I can dimension between the two opposing faces of the cylinder head support. And you'll see the user interface of the Semantic Tolerance Advisor is identical whether at the assembly level or the part level. And here we're creating a reference datum feature, and here I also want to create a coaxiality condition. But we don't see coaxiality in the Semantic Tolerance Advisor. Why? Well, because the two holes are not coaxial. So we need to make a modification. So the Tolerance Semantic Advisor has enabled us to detect the misalignment. So we update the complete assembly based on the part modification. And now when we reselect the hole, you see that this time we find the coaxiality. So it is more than an advisor. It's an enormously powerful analysis tool, which enables earlier identification of errors even at the level of the assembly. So let's summarize. What value did we bring to the detailed design phase? So first, we're improving the quality. We're working on 3D geometry, and there's no misinterpretation. Errors are identified early. Second, product accuracy is improved due to the 3D access. And one of the impacts is that of cost reduction. It can also be reused by any process, and reuse of functional descriptions among part families. So now let's look at the experience phase, sometimes called the review phase, where many users can experience the product. And here you can see how our 3D experience platform brings value across many disciplines. The scenario here continues from the detailed design of the bracket, and it will show the synchronization of two disciplines, mechanical and electrical. Here, in parallel, as the mechanical designer was designing the bracket, an electrical designer designed the wire harness and cabling. As you can see, because of the bracket, there's now an interference. The mechanical designer, by accessing one single environment, has identified that there is a problem. He connects to his colleagues and shares in real time with what we call real-time collaboration, the fact that there is an interference. The cost of modifying the bracket is higher than simply moving the electrical connector position, so he asks his colleague to agree to move the connector. So by simply moving the connector, the interference is removed. So this illustrates the tremendous capability of real-time sharing and collaborating, and how it allows early problem identification and resolution. So the value here, of course, is that the product definition is available to anyone, anywhere, anytime. One single source of product information and one single source of errors. Second, we can support multiple disciplines, here between mechanical and electrical. And we also showed real-time concurrent design and review. And the result of all the above is that decision-making, error detection, and error resolution are all dramatically accelerated. Now we move to the manufacturing phase, and here there are two aspects. The first of which is the ability to produce and manage drawings to support traditional processes, but maintaining our single 3D reference. This is what we call 2D layout blueprint. We have the 3D bracket definition, designed by the detail designer. And even in this single 3D environment, we can create a 2D drawing. So we have the frame and the title block, and we can directly populate our views from the 3D captures which have been created in 3D. The front view, the section view, and so on. We're not extracting any drawings here. We're just creating what we call 2D layouts in the same 3D environment, and we can print it directly. If people still want to have an isolated drawing, or a DXF for example, we're able to do so by simply generating the drawing from the 3D. So we're not missing any process coverage. We can still connect to any existing manufacturing processes which use 2D as their reference. But what is particularly important is that we can directly reuse the 3D data in manufacturing. From the tolerance and semantic definition of the bracket, we can define the manufacturing environment that will propose and enable semi-automation based on those definitions. So we're going to capture some knowledge in the standard process from the definition of tolerances. For holes, for example, such as the slot, we know there is a proposal linked to that. The way the hole is defined is linked to the way the resource is provided. So here we retrieve the traditional complete machining operation. This can be available for any manufacturing process, and the user makes a choice of which he wants to run. But at the end there's a different proposal which is linked to the 3D geometry definition, and some semantics may have an impact on the process in a semi-automatic way. So we complete the operation, and now we will directly work and simulate with different tools and different paths using the processes and resources that are requested to manufacture this bracket part. So here you see the simulation of the toolpath directly on the 3D geometry, with the change of tools and the simulation of material removal. So again, this approach is to promote the continuity of the process from 3D into manufacturing, and showing that we are also bringing value in contributing to the overall process. So the value in manufacturing includes on-demand blueprint generation, either linked or not, and we can directly connect the manufacturing to the 3D geometry, referring to the semantic definition to accelerate toolpath definition. Now let's move to production, and I want to focus on just one aspect of the many things we can provide here, and which is linked to our original 3D master data. So from the original detailed design of the bracket, with captures we're able to filter the elements we wish to provide to a supplier, for instance. And that model then is extracted in 3D to be sent to the supplier or the reviewer, ensuring that only the information that you choose to send is provided. So now I'm in the role of the guys doing the review or the production, and they can simply select the captures or views which are the ones designed for him and easily available, as you can see on the screen. So in production, 3D leads to a better understanding and removes misinterpretation. IP can be protected by filtering what you want to export to suppliers or to anyone else who wants to look at your data. And finally, everyone can directly access the single definition of the product. So now let's look at some cases where our customers are improving their performance with 3D Master. Gulfstream have created an end-to-end model-based definition approach to the design and development of their aircraft. And in the United States, model-based definition is the term used typically to replace 3D Master. At Gulfstream, a full 3D definition is employed to all users. Their initial implementation was for interior outfitting. On their new G650 aircraft, the entire airplane program uses the 3D Master approach. Often regulatory bodies can be conservative, but Gulfstream worked with the Federal Aviation Administration to gain their approval of this approach. So Gulfstream have seen a productivity improvement in some areas of over 40% and have nearly doubled the delivery rate of aircraft while maintaining constant cost. And here's an interesting comment from the customer. They were originally concerned about the downstream acceptance of the 3D approach, and they were pleasantly surprised to find that technicians adapted to 3D Master much more quickly than they expected. Goodrich deployed 3D Master in the tooling design process in their aerostructures division, and competitiveness was the main driver, targeting a 30% reduction in tool design cost. But they recognized that they didn't simply want to pass cost on to their suppliers. So they involved suppliers in the process and the cultural change that needed to take place across the value chain, and the benefits were worth it, a 20 to 30% saving in design cost. Also, the elimination of redundant data and effort, and the single source of data clearly minimized errors. In Europe, Saab Aerospace are both an aerospace OEM and major supplier. Using 3D Master, they've been able to achieve a reduction of 90% in change costs and have delivered 3D work instructions to the shop floor. Time spent creating drawings is now a third of what it was previously. Ford have deployed 3D Master and have reached out to their extended enterprise with a communication and recommendation to the supply chain to adopt 3D Master themselves, targeting over 500 suppliers. Here we have just a small number of our customers who have deployed successfully 3D Master. Boeing developed their most recent aircraft using this approach, and PSA expect to achieve 2-digit productivity gains. And VW improved their decision making and collaboration and production using 3D. So if we have to summarize all we said during the presentation, first, one of the most important things is that we have access to the correct information at any time, anywhere. And the productivity improvements from simple information access is critical here. There's also a natural path to go from 2D Master to full 3D Master, and it improves product and process quality, as we've shown. The big direct impact is cost reduction, of course, and the savings achieved by customers who have deployed 3D Master are huge. And also we're respecting the standards in the industry for the representation of information. More and more, 3D is becoming the contractual data set. So the cost reduction and the quality improvement are available for all customers who deploy 3D Master. And finally, we also have to consider and manage what it takes to make a successful transformation. How do you get from what you have today to what you target? And it's important to determine the objective and which phase to target initially, and to identify what changes are necessary, whether they be technology, process, or cultural, across the value chain. Dassault Systems consultants are skilled in what we call a business value assessment, which can assist in planning and achieving this transformation.